We now begin a series of lectures where we calculate the electric field due to various types of charge configurations. These charge configurations are important for different reasons. We'll explore those reasons as we proceed. Specifically in this lecture, we'll take a look at the electric field that is due to what is called a dipole. A dipole consists of two charges, one positive and one negative. They have the same magnitude and they're separated from each other by some distance in space. I have this written out for us as a problem, and there is a diagram associated with this problem. Go ahead and access the problem and copy it into your notes as I read it to you here. Okay, find the electric field at point P. Remember that the point in space that we're always trying to calculate the electric field at is always referred to as point P. So find the electric field at point P. This configuration is called a dipole. Each charge is a distance A from the origin, and point P is a distance x away from the origin along the x-axis. So the diagram then, therefore, that's being referenced here looks like this. Okay, so let me go ahead and draw in a coordinate system like so. And then right here is our point P in space, a distance x away from the origin. Okay, and then we have our two charges. One negative, a negative q, another positive, a positive q. They're separated from each other by a total distance of 2a. So then therefore on the diagram, this distance here is a, as is this distance here. Okay, and now what we do using the formal vector notation is we find the electric field at point P in space, first of all due to the positive charge, then secondly due to the negative charge, and we add the two electric field vectors together to get the net electric field at point P. Okay, so let's see what happens first of all due to the positive Q. Okay, so E due to positive Q. So we have to run through, of course, the formal vector notation here. Let's get all of our position vectors. Okay, so first of all, little r. Little r, if you recall, always goes from the origin to point P in space. So in this case, it's just xi hat. Okay, then little r prime always goes from the origin to the charge that causes the field. That's going to be a j hat. Okay, and then capital R is r minus r prime. So that's equal to xi hat minus a j hat. So I'm not going to draw it on the diagram, but capital R vector goes like so into the fourth quadrant, positive x component and negative y component. That's right here. Now it's just the hypotenuse, of course, of a right triangle, so finding its magnitude just involves a little bit of Pythagorean theorem. So the magnitude of capital R is going to be x squared plus a squared to the 1/2 power. Okay, and now we just plug everything in to the expression. So the electric field at point P due to the positive Q is going to be K times the positive Q times capital R vector xi hat minus a j hat, and then divided by this magnitude of capital R cubed. So x squared plus a squared to the 3/2 power. Okay, now let's look at that electric field vector at point P in detail. Notice that it points in the positive x and negative y direction. Therefore, it is a fourth quadrant vector. That then looks, say, like this on the diagram, like so. So this is the E due to Q. Okay, now we repeat the calculation, but in this case, what we're going to do is find the electric field at point P due to the negative Q. So once again, I have to set up all of my position vectors. Let's go ahead and do that. So now this is going to be E due to minus Q. Okay, once again, little r. Notice that I've left it here on the board from the previous calculation because it's the same thing. That is, little r always goes from the origin to point P in space. Okay, and then we've got little r prime. Little r prime goes from the origin to the charge that causes the field. That's negative a j hat, like so. Okay, capital R vector is r minus r prime. So xi hat minus a negative aj hat is xi hat plus aj hat. Notice that this right here is a first quadrant vector. It points like this on the diagram, like so. The magnitude of it, of course, is found once again from Pythagorean theorem. So capital R, magnitude is x squared plus a squared to the 1/2 power. Okay, and now we just plug in. So K times negative Q, once again this charge, remember, is negative, and then multiply by capital R vector. So xi hat plus a j hat, and then divided by magnitude of capital R cubed. Like so. Okay, now let's see what that vector looks like. Negative sign, negative x component, negative y component. That means it's a third quadrant vector. It points like so back towards the negative q. So right here, like so, that's kind of a lousy marker, like so. This right here is e due to negative q, like so. And now we're going to add these together vectorially. Notice what should happen when we add the x components together. When we add the x components together, they should cancel out. And in fact, they do. Right here is a kqx for the x component. Right here is a negative kqx for the x component. So then therefore the x components cancel out. This then means that the net electric field at point P in space is going to be in the negative j hat direction. Let's go ahead and get that description. Okay, so I'm going to erase some stuff here. Let's get rid of these guys. Like so, and then let me do this on the lower board. Let's go ahead now and calculate the net electric field. We'll just refer to that as E. Okay, so as I mentioned earlier, the x components of this electric field and this electric field cancel out, and then therefore we're going to have the following. Negative kqa j hat over the denominator, and another negative kqa j hat divided by the denominator. Once again, there are two negatives being added together here. So I want to add up, I get negative 2 kqa j hat divided by the denominator. That is like so. So on the diagram above, at that point in space, the electric field itself points in the negative j hat direction. That's the net electric field. So the net electric field at point P in space on the diagram above looks then something like this. Okay, let me once again do some erasing here. And let's get to here once again. And now I'm going to start moving some terms around a little bit, specifically in the numerator of the expression. Let me write the numerator of the expression in the following way. Negative k, and then 2aq, I'm going to put in parentheses, multiplied by j hat, and then divided by the denominator. Okay, my reason for moving terms around here, specifically in the numerator of the expression, is to get this new quantity, 2aq. This new quantity, 2aq, is given a name. It's referred to as the dipole moment. So let's now go ahead and define what's called the dipole moment. It's referred to as small p. It's equal to, by definition, the distance between the two charges, 2a, multiplied by the magnitude of the charge. Okay, now before I describe exactly what it is that we're defining here, let's check the units. It is, after all, a new quantity. So we have coulombs multiplied by a distance in terms of meters. The units are coulomb meter, like so. Okay, now let me just write out the electric field now in terms of this new quantity in the following way. Like so, and then when you write it like this, notice that the numerator of the expression is actually describing a vector. The dipole moment is a vector. By definition, it goes from the negative charge to the positive charge on the diagram above. Therefore, in vector form, we can write the numerator of the expression like so. where now the P vector, the dipole moment vector, well, that points upwards on the diagram above, but the negative sign from our calculation gives us the electric field vector in the negative y direction on the diagram above. Okay, now why do we bother going through the last couple of minutes here of this lecture to define this new quantity called the dipole moment? Well, let me go up to the diagram above. Okay, the dipole moment P is 2a times q, and on the diagram above, it specifically now points in this direction, from the negative to the positive charge like so. This right here is the P vector. Let me give you some context as to why we bother to describe or define this new quantity, the dipole moment. Let me give you an example that you're familiar with from chemistry. Back in chemistry, for example, you talked about the polarization of a molecule. Let's use the example of water. Okay, now recall, of course, what a water molecule roughly looks like. It looks like little Mickey Mouse ears, if you will. So we've got the two hydrogen atoms like so, and then those two hydrogen atoms are sharing a covalent bond with an oxygen atom like so. You've got positively charged protons, for example, making up the nuclei here of the hydrogen atoms. You've got protons making up the nuclei here of the oxygen atom. However, as an average, the electrons spend most of their time, if you will, within the molecule, kind of on the bottom half of the diagram. The bottom half of the molecule is negatively charged, and then because the electrons are spending most of their time as an average down here at the bottom of the molecule, this then means that up here at the top of the molecule, because of these protons, this side of the molecule is positively charged. Refer to this splitting of the charge as polarization. Mathematically, however, we describe the amount of polarization by using this new quantity called the dipole moment. In other words, the water molecule itself mathematically behaves as the dipole moment vector up on the top diagram. It's like a little stick, if you will. That's kind of like how I think of it. The dipole moment, like so, has a positive side to it and a negative side to it, and the length of the stick here is essentially describing the amount of polarization, and the positive side and the negative side also describe the amount of polarization. So then therefore, a polarized molecule can be mathematically modeled by using what is called the dipole moment. Okay, let me now show you an example as a demonstration here of the polarization of a water molecule. Okay, as a short demonstration, I need to tilt my phone, so bear with me here as I do. Okay, I'm going to point my phone here towards my sink that I have here at the side of my desk. Let me go ahead and move the phone a little bit like that. Once again, bear with me here as I do this. Okay. Okay, now let me go ahead and turn on the sink here, the faucet. Let me get a nice stream of water. Okay, now what I'm going to do is charge up this plastic rod through the process of charging by friction. So I'm going to give the plastic rod an electric charge. There is, of course, an electric field associated with that electric charge. The electric field associated with this guy's electric charge, well, that then will ultimately cause a force to be exerted upon each individual water molecule because each water molecule has a dipole moment vector associated with it. Let me go ahead and get this as a nice straight stream of water. Like so. And now let me do the following. Like so. See how the stream of water is attracted towards the charged stick? Like so. So what you're seeing here is an electric field caused by the stick having then an effect on each individual water molecule, like so. And we can easily see that effect because the water molecule itself has a large dipole moment vector. Okay, let me tilt the phone back. Like so. Bear with me here as I do. Let me tilt it up as well. Like so. Okay, lastly, about this lecture involving a dipole, you have to be familiar with the general shape of the electric field associated with a dipole. Now, what we did in this calculation was we only calculated what the electric field looks like at one individual point in space. If you did this, however, in 3 dimensions around the entire dipole, you would then end up with the overall shape of the net electric field due to that dipole. The net electric field looks like this. Okay, so let me just go ahead and draw the dipole itself like so. Here's the positive side and here's the negative side. And then the electric field lines look like the following. Let me use a different color here. Like so. So from the positive side to the negative side is an electric field line like so. And then symmetrically, like this, from positive to negative on either side. And then let me draw a few more electric field lines flaring outwards like so. Like so, where all these electric field lines like so go from the positive side to the negative side. Once again, the positive side of the blue dipole moment is here, whereas its negative side is here. So this is the overall shape of the net electric field due to a dipole. Okay, that concludes this lecture on dipoles.